Hi there and welcome to the second workshop for 161122 statistics. So today we're going to follow on from where we sort of left off last time and look at a few different geometries that ggplot can give us. So I'm just going to start by running the code we have here, and we'll get our plot that we had last time. Okay, and now we're going to experiment with this by changing the geometry. So another geometry that we can use might be geom bin 2D. So let's try that, see what that gives. So you can see here that what this does is it divides the x and the y scales up into little squares. They're kind of like pixels on a computer screen, and then it counts the number of observations that fall in each of these squares, and that's what's then shown with the colour. So you can see that the most earthquakes are down this part here. So this is showing us that most of the earthquakes, or a bunch of earthquakes, occur along a line around 180 longitude. We've also got density 2D that we might try. And so what this does is essentially it gives you like a topographical map of where the observations are. So if you like, what it's doing is it's sort of counting the number of observations in each area and sort of stacking them up, a bit like we were doing back on the bin 2D one. But instead of it being all chunky like this, it smooths across everything, so that we get sort of smooth hills rather than very sharp angles. And it does that basically by putting sort of a little bit of, it's like a little blob of jelly on each point, and when 2 points are close to each other, the two blobs of jelly sort of add up. And so I'll give you a demonstration of this in lecture 3, so you can, of how a density estimate is built up. So this is done by popping a little blob of jelly on each of the 1,000 points, where points are close to each other. The jelly accumulates into mountains of jelly. Okay, that's the idea. And so there's lots of other potential geometries that we can use. And we don't have to just use one, we can do more than one. So for example, I can do the points and then put the density on top. Okay, so we have this here where we see the actual underlying data, and we have the density. And as you can see, it's where the observations of highest density are is where the hills are. So this, if you like, is because there's a lot of lines very close together, where it's a very steep hill here. So there's a lot of observations all around this area here. And similarly, there's more observations along the spine here of this area over in this direction. Perhaps in order to see things a bit better, we might add some alpha to that, to the points, maybe even a bit more than that, just so that we can sort of get a feel for where the density is. There you go. Now obviously we can change some of the features of these lines, just like we can change features of the points, which we did last time. So for example, we can change the color easy enough, so we can make it say dark red. So there we go, it's dark red colors. We could also change the line type and the thickness of the line. So I think the thickness of the line is maybe size. Yeah, well, that's a little bit over the top, but perhaps we want nice thin ones. There we go. We can do that as well. And there's other ones that we can find by looking in the vignette we looked at last time. Am I going to get this right in one go, or am I going to have to look up the help? I'm going to have to look up the help, aren't I? So let me look up. I found it, the help via G on point. There, that's the one I wanted. So we can change the color with col or color. So both the US and UK spelling will work, as well as the short form. The width of the lines specified with size, and the vignette can tell us more. So let's have a look. Let's click run the vignette command. Here we go here. So if we look at lines, we've got line type, and so the line type is specified. Let's have a look how it's done. Line type, and these are the various line types you can have. So we've got solid, dash, dotted, dot dash, long dash, and so on. So to use dashed lines, we would do line type is dashed. And there we go. I perhaps want a slightly thicker line so that we can see them. There we go. Okay, so that's how you change the aesthetics of the contours. The other thing that we can do is we can adjust the amount that things have been smoothed. So I'm going to switch back to normal lines, so solid lines instead of dashed. Okay, so the default smooths based on some criteria that tends to work well, but is nonetheless somewhat arbitrary. So it's not completely arbitrary, but it's sort of been optimized for certain types of data, and not all types of data will the default smooth work well. And so we can adjust the amount of smoothing via the adjust parameter. Default is 1, values less than 1 will smooth less, and values greater than 1 will smooth more. So let's have a look at an example. Right, let's smooth less. So less smoothing. Sorry, I need to actually adjust the adjust. So you can see here that that this is a lot less smooth, and we're capturing the areas of high density perhaps a little bit better. Okay, but it's quite noisy in the sense that we've got 3 independent peaks here, whereas perhaps this is actually sort of a smooth ridge, which we're not seeing as well perhaps. Okay, or we could do more smoothing. Okay, and you can see that we've lost a lot of detail here. It basically is saying that there's two hills in this data, one here and one here. Okay, so the sort of the centre of the hill is here, but now we've lost the fact that we actually have a ridge running along here. Whereas at least this was somewhat captured by here, but we were sort of introducing these individual spikes, and perhaps we still had the ridge showing up here, but perhaps we were losing a little bit of content in the middle here. Okay. So these smoothing amounts are somewhat arbitrary, and usually what I do is just mess about until something looks good for what I think the data looks like. Okay. There's not necessarily a right or wrong answer, although I would suggest that this is probably over-smoothed, and similarly this is under-smoothed. What you're looking for is something that's sort of somewhat pleasant to the eye. Okay, is the idea. So when we smooth a little bit, i.e. adjust less than 1, then our density estimate follows our data better, and when we smooth a lot, just greater than 1, then our density estimate starts if you like, it's smushing, technical term, the data, so we're not really capturing the data intricacies or detail. Okay, so when we smooth a little, we capture a lot of detail, but when we smooth a lot, we sort of miss the detail, right? We're sort of blurring everything, essentially. So you might think that, well, we should always smooth not very much, right? We should always opt for this type of setup. But that's not the case, because the other thing that you've got to care about is the fact that you very rarely have all of the data, right? You usually only have a sample of data. And so the other thing you've got to think about is what happens when you collect a new sample. So this is earthquakes around Fiji. There's 1,000 of them or whatever. Obviously, these are earthquakes that happened in the past, and so we could start collecting earthquakes from now for the next 10 years, say, and we'd have perhaps another 1,000 earthquakes or something to look at. But those future earthquakes are likely to be in slightly different regions. They're not going to give us the exact same points, right? It's going to be slightly different. So hopefully it'll be generated from the same process, so whatever is causing the earthquakes is probably unlikely to change too much, perhaps in the space of 10 years or whatever. So we might expect that the underlying trend will be the same, but the actual individual points that we end up sampling might not be the same. Okay, so when considering sample to sample variation, if we smooth only a little, then the two surfaces, then the density estimate from the two samples may differ potentially quite a bit. As the two samples will differ a little bit. If we smooth a lot, then our sample to sample variation will be expected to be small. So sample to sample variation of the density estimate will be expected to be small, because the smoothing, so any differences will be smoothed over. Okay, so there's a trade-off here, right? smoothing a little bit gets us closer to the data. But it might mean when we get a new sample, our trend from the density will differ a bunch. Smoothing a lot will leave us further away from the data in front of us, right? Because we're essentially we're sort of smushing over it, and so we're not picking up the detail. But the sample-to-sample variation will be low. So this is known as the the bias variance trade-off. And it's a key concept in statistics, in that basically everything that we do, or all the modelling sort of stuff that we do, will have a trade-off between bias and variance. So the idea is that as you get closer and closer to the data, when you get a new sample, your two estimates from your two models that are being fit to those separate data sets are going to differ quite a bit, because the underlying samples differ quite a bit, right? Whereas if your model is actually sort of smoothing over some of the detail in the data, then your models will actually look quite similar from two different samples because of that smoothing effect. Okay, so the smoothing effect introduces bias because you're no longer actually picking up the signal very well. You're not getting into the details very well. You're losing the detail because you're smoothing over it. But on the other hand, you then reduce the amount of variance from sample to sample. So your model estimate does not differ as you start collecting more data. Okay, so if you have a model that has a lot of detail in it, then it's going to fit one particular data set really nicely. You're going to get the signal, but when you then introduce a new data set, again, you're going to fit really well to that one, and the two model fits are going to differ because they've both been sort of overtrained, if you like, or focusing in on the detail of two separate data sets, and that detail is changing because it's been generated by noise, by the underlying sampling process. Okay, so the idea is that when I look at this, I see a noisy signal. I see lots of peaks in various places and sort of oddly shaped contours and whatnot. You know, it's saying that there's a separate bump out here and another bump here and so on. When I look at this, I immediately see something that is too smooth because it's not picking up the detail. I can easily see the detail in the points here that, that doesn't follow this single hill hypothesis, if you like. And if I skip back to this one, then this one's actually a reasonable balance, right? It is saying that I've got some areas with slightly increased density about, and it is picking up that there's sort of a ridge along here. But it's not going into too much detail about that. Okay, so that's the idea of the bias variance trade-off, and we'll see it again and again as we go through things. Okay, so we might end by sort of tidying up the, so I'm going to go back to adjust equals 1, and then we'll tidy up the axes. I'm just going to adjust equals 1, so there's the adjust equals 1 case, and I'm just going to tidy up the axis. So our x-axis will be longitude, our y-axis might be latitude. Okay, and I might want to add a title as well. Earthquakes along Fiji, around Fiji. Something like that, right? And you can get a more interesting one if you want. So for example, we might add a subtitle that might be many earthquakes are focused occur along a ridge around longitude 180. For example, whoops, I didn't finish with a bracket there. Okay. Okay, so for this next bit, we're going to improve a plot. Okay, so here's the plot here from the question sheet, where we've got a plot of magnitude versus stations. Okay, and so there's a couple of things that we notice when we look at this plot. The first thing we notice is that there's a trend up, right? A trend that sort of makes sense. So this is the number of stations at which an earthquake was detected, and this is the magnitude of the earthquake, so the size of the earthquake, if you like. And there's a natural increasing trend which makes sense to us in that the bigger earthquakes are going to be detected further away. So there's going to be more stations, more earthquake detecting stations that are able to pick those earthquakes up. So that's the increasing trend there. And the other thing is that there's vertical stripes, right? And so the vertical stripes are from the fact that the magnitude is only defined to one decimal place, right? So we've got 4.0, 4.1, 4.2, 4.3, 4.4, and 4.5. Okay, we don't have 4.43 or whatever. So either it's been rounded, which is probably the case, or for whatever reason, the equipment is only spitting out the magnitude to one decimal place. So what this means is that it's hard to tell exactly what the density is of points is down the bottom here. For example, we can't really tell if sort of the middle of the data is actually up here somewhere, and that most of the points are up here, and it's just that we've got quite a few down here. It basically looks a similar level of density all the way across, which might mean that the number of points here is sort of uniform. But that's probably not the case, but we can't tell from here. Okay, so there's a couple of ways around this. I think there's two ways, one of which is better than the other. The first thing we could do is, we noticed that the magnitude variable has been rounded. This has led to overplotting. So that's the phenomenon where points are being plotted on top of other points and are distinguishing them. For example, this point up here, potentially there could actually be 10 earthquakes stacked up on top of each other there, and because they have the exact same magnitude and the exact same number of stations, we can't tell that there's 10 points there. Or there could just be one point there, right? Or there could be 3,000 points there. We don't know, right? Because of the rounding effect. So the number of stations is obviously a whole number, so that's sort of rounded in some way. Admittedly, there's a big scale here though, but the magnitude is also rounded. Okay, so one way we could fix that is to use some jitter. So let's just try putting jitter as is, and you can immediately see what's happened is that each of the points has moved a bit horizontally and potentially vertically. So by default, the jitter geometry will add some noise to the data to move them around a bit. And by default, the amount of noise that it adds has to do with the resolution of the data. So essentially it works out the smallest difference between the magnitude, which in this case would be 0.1, and it adds, I think it's about 80% of that. Let's have a look in the help for geom jitter, see if we can figure that out. It'll probably say here somewhere. I think it's in the width. Amount of vertical and horizontal jitter. The jitter is added in both positive and negative directions, blah, blah. If admitted, it defaults to 40% of the resolution of the data. This means that the jitter values will occupy 80% of the implied bins. Okay. Right. So what's happening is that it's 40% of 0.1 is the amount that it can move left or right. And it does it both ways, right? It's added in both the positive and negative directions. So if we go back to our plot, so 4.0, it could be up to 4.0 plus 40% of 0.1, which is 0.04, so it could be up to 4.04, or down to 3.96. And this category here would be from 4.06 to 4.14. Okay, so there's a small amount of gap in between each one. It's just hard to see, of course, because of the size of the points. The radius of the points would then add on to that. But nonetheless, you can still detect the striping if you, at least if you know about it. I'm not sure if you detect it if you didn't know about it, perhaps. Now, the problem here is it's added jitter in both the X and the Y direction, so in both the magnitude and the stations, it's added jitter. And we can change the amount of jitter with the width and height. So the width, of course, is oh, look at that nifty pop-up help thing. The width would be the amount of jitter in the magnitude variable, so we want that to be, say, 0.04, and we want the height to be maybe 0 so that there's no jitter in the Y direction. Okay, so each time I run this now, the Y coordinate of the points is not changing. So if you, for example, focus on this one here, right, if you look at its Y coordinate will be the same whenever I rerun that line of code. It's just the X coordinate is moving about, right, randomly due to that random noise. We could do a little bit less width if we want. Okay, so now you still see the striping, but perhaps can detect where the density is. Or maybe we don't mind if things cross over a bit by making a, using 0.06 means that the 4.0 could go as high as 4.06. The 4.1 could go as low as 4.04, so we've mushed them together a little bit. But nonetheless, we can see the trend a bit better on this plot than we could on this one, right? Because you can detect the density, where the actual trend goes. That's the idea that we're trying to get to. Nonetheless, we have added some sort of fake data here, or we've modified the data here. So the other way that we can get over, we can get around overplotting, is to use transparency. So jitter adds some random noise to the data. Useful if the data has been rounded. Particularly if it's being rounded artificially. Nonetheless, this is altering the data, so should be used with caution. The other option to deal with overplotting is to use transparency. Right, so what we're going to do is we're going to switch back to the point, and of course you can combine the two things as well, but we're just going to add some alpha. Right, and this then allows you to see where the density is. Right, so it's actually through here. I think you'd probably actually want to combine the two ideas, so perhaps in the end I might do we might do some jitter only in the X direction, which is the one we know has been rounded. The Y direction has not been rounded, it's a whole number anyway, right? And perhaps would limit it a little bit, and would add some alpha. Okay, maybe I would just increase, there we go, maybe I would go something like that. So I'm applying some jitter. You can still tell that these bands, okay, but you can then see the trend. That's the idea. Okay, what about adding some smoothing? Okay, so there's two that are recommended for us. We could try the density 2D like we had before. We're going to have to specify the mapping. So there's the density 2D. So that's just showing us that most of our earthquakes are down here. But that's kind of not really the best way to smooth this data. So this shows areas of the XY grid that have the most points in them. Right, so the most points are down here in this sort of we've got a bulge of data. In this case, we probably want the trend in the data instead, which geom smooth gives us. Okay. There you go. Okay, so this is sort of the average increase in number of stations for a given magnitude. Okay, and just like with the density smoother, the density 2D smoother, we can mess about with how smooth the geom smooth is. So to do this, we switch the type of smooth and then adjust the type of smoother to a low S and adjust the span. Right, so let's do that. So we're going to use method equals low S. Okay, so you'll notice that we get a slightly different smooth, and it's just so the two smoothing methods just use a different bunch of underlying assumptions. So the default smooth method, when you've got more than 1,000 points or 1,000 or more like we have here, it uses what's called a generalized additive model, or a GAM. So if you've seen the output before, you can see it's method equals GAM. Okay, and by default that uses a set of splines. So it's a bunch of cubic splines that it fits through the data. So essentially what you do there is you define a bunch of you sort of split up the range of the magnitude, and you estimate a cubic across, I guess it's 4 points. 4 points. Yes, 4 observations. Every 4 observations or 4 spacings, you fit a cubic such that they all give you a smooth curve. Okay, so just a way of finding a smooth trend through data. So it's a cubic spline. A low S instead is a local linear smoother. So what that does is it's basically like fitting a regression line. Okay, except that regression line is defined at each X location. So in this case we've got magnitude, so we start at magnitude 4.0 and we're going to fit a straight line through the data centered at 4.0. Now to do this, we don't want a straight line going directly up, right, all the way through the data. Instead we want to sort of pick up the local aspect of whatever the trend is. So we want the slope of the line and the position of the line to reflect the data that's around 4.0, rather than it being influenced by earthquakes with large magnitude. Okay, so essentially what it does is it sort of uses the first say 70% or 50% of the data. We'll modify that in a moment. I think by default it uses the first 75%. And it weights the data such that the observations that are close to 4.0 are more important than the observations that are far away. And the idea being that basically you end up focusing on the observations that are down here, and you fit a straight line through those points. You then move up a bit, so say to 4.2 or 4.3, and you do the same thing. You fit a straight line through the points, with more weight or more importance to the points that are around magnitude 4.3. Okay, and so that would have a slightly different slope because the underlying trend will slowly change as you move across the range of magnitude. And eventually you get up here and you do the same thing. So when you're up at magnitude 6, you again are fitting a straight line through the data, and you're prioritizing the points that are around magnitude 6. So your slope and your position of the line here is capturing the trend up at this end of the magnitude. And then you just sort of stitch them all together and you get a curve. Okay, so that's what's going on there. And so you can alter the amount of smoothing that's done by altering the span. So the span by default is 0.75, which is basically means that it's using 75% of the data. So when you're down this end, you're basically ignoring the top 25%, and you're using the first sort of 3/4. And when you're up this end, you're using the 3/4 from that end and ignoring the quarter that are down with magnitude 4. Okay, and you can muck around with that value. So if we make it less, then we're going to smooth a bit less. So you can see it curving over towards this point here. Okay, that's another example of the bias variance trade-off. The idea is that as you reduce the span, you're going to introduce more noise, because as you reduce the span, you adapt faster to the data. But if the data is noisy, which generally data will be, you may end up adapting to that noise. And so you may end up, in some circumstances, not in this one by the looks, you may end up getting something that's a bit too wiggly. Okay, whereas if you smooth more, then you are essentially eliminating the noise, but you may not adapt quickly to the data, so that the trend will change slower, and therefore your trend will be further away from the true trend. So it's again a trade-off, right? If you smooth a bunch, then you're going to reduce the sample-to-sample variation, but you're also not going to capture the true trend very well. If you smooth less, then you'll be slightly better at capturing the true trend, but you're also going to be susceptible to introducing noise, and your sample-to-sample variation is going to be higher. So there'll be some sweet spot in between. Okay. And lastly, we may want to tidy up the labels. Okay, and add a title, larger earthquakes are detected at more stations. Okay, there we go. Alright, so that's the idea. Feel free to have a play with the span, or play around with fitting, with messing about with the colours and all that sort of stuff, in order to get a handle for the sort of things that you've got control over.